Hi, again, this is my video number 15, I think, yeah, number 15, yeah. So, in the last video, I have explained the non-autonomous system. Also, I've given the theorem that relates between the autonomous and the between the linear system and non-linear system of the autonomous system. Okay, now I want to give the example. How can we deal with the non-linear system? Okay, so consider the motion of a pendulum. Yeah, motion of a pendulum. So for the pendulum, the equation is given by, we have theta dot plus 2k theta dot plus q sine theta 0, where k is positive and q is positive. Then if we do the substitution, x equal to theta and y equal to x dot equal to y. So what we have theta double dot here, so I can differentiate that twice. So x dot, that give you theta dot. Alright, so theta dot give you so x dot is y, so this is equal to y. Okay, then if I differentiate this again, theta double dot, that give you y dot. Okay, if you substitute all this into the equation, so what we have is that x dot equal to y. So then we have x dot equal to y, and here you have x double dot is y dot, so we have y dot plus 2k theta dot is y plus q sine x theta, so theta is x, that equal to 0. So I can write that system becomes x dot equal to y dot is equal to minus 2k y minus q sine x. Alright, and I can write this to have a x in front of it, so I can write this as a negative. So I have q here, so I can write as a negative qx minus 2ky minus q, I can take it out, so we have x plus so minus, so I think this is plus x, so minus sine x. Okay, so that system we have now our system become x dot equal to y and y dot equal to minus x minus 2ky plus q and everything. Okay, so that's how we have the system. So if you can find the critical system for that, for the critical points, yeah, for the critical point, so what we need to do is just equate that p and q equal to 0. So we have y equal to 0, and the other one we have minus qx minus 2ky plus qx minus sine x, that give you 0, to find the critical points. Alright, so you solve these two equations. So we have y equal to 0, that one is 0. Then what left is negative qx equal to all those things. You can take out x, then we can have q sine x equal to 0. Q sine x equal to 0. Then you can find what sine x, make it x sine x equal to 0. Then you can find what the critical point there. So therefore, the critical point you can find, let me write here, this one, that if you solve this, there's question out q cannot be 0, so you have sine x equal to 0. Alright, so you have x equal to basically plus minus n pi, right? For n equal to from minus 0, 1, 2, 3, and so on. Okay, now having done that, you can have the critical point is given as, so therefore we have the critical point is given as those x and pi and y. Sorry, y is 0. That's the critical points. Yeah, for n 0, 1, 2, 3, and so on. So for the case of we want to do we want to sketch the trajectory for that. I think enough for if you consider only 2 points. You can have more than 2. Just for this example, I just want to show you 2 points. Yeah. So, and if you look at the system that we have here, that system, we have our zeta 1 is 0. Sorry, our epsilon 1 is 0. Our epsilon 2, this is our epsilon 2. Alright, this is our epsilon 2 here. This is epsilon 2. And epsilon 1, this part here, this is 0. Alright, so we have epsilon 1 is 0. Epsilon 1 is 0, and epsilon 2 is q x minus sine x. Okay, and this epsilon 1, epsilon 2 satisfy those three this system, the nonlinear system here, as well as epsilon 1 and epsilon 2 satisfy the 3 conditions that I mentioned earlier. Okay, so we have, what is those conditions? We have PQ, where this is our P, the whole thing's on the right side of X, this is P, the whole thing's on the right hand side of Y, this is Q, so P and Q must be continuous, and as well as its partial derivative must also continuous. So that's the first condition. The second condition is, you look at here, we have AX, what is it? AD minus BC, that's different than 0, also satisfied. And the third condition, if we take a limit of zeta I over R, so epsilon I, which is now epsilon 1 is 0, so of course for the first case it will give you 0. For the second case, you have take a limit of epsilon 2, which is qx minus sine x over R. If you take that, that also goes to 0. This is not difficult to see those things. Okay, so this epsilon 1, epsilon 2 satisfy the 3 conditions, 1, 2, and 3. Yeah, condition near the critical points, near x equal to 0. So for this reason, since it satisfies 1, 2, 3, so which means that 0, 0 is simple critical points. So 0, 0 is simple critical points. Okay, now if you consider the corresponding linear system, the problem with it that I not realize is goes beyond than that. So let's write that. Sorry. This thing, okay. The corresponding linear system is given as we have x dot equal to y and y dot equal to minus qx minus 2ky. Now you can deal with this linear system as before, which is determine whether it has a absolute critical point, all those conditions, you know. So in this case we have, let's say right here, let's say in this case we have A, so we have A equal to 0, B equal to 1, our C is minus Q, and our D is minus 2K. Okay, so if we find the roots of that and take the second part where we have A minus D squared plus BC for BC. Yeah. So this equal to 4K squared minus 4Q. And as well we have A plus D, this is equal to minus K. Since K is positive, so this is negative. So we have the condition for A plus D is negative, A plus D negative. We have, you have to look at the notes. Where is it? A plus D is negative, so we have A plus D is negative. Where is it? One. So A plus D negative means we have both roots are negative. Yeah, we have both root negative. Both root negative. Okay, now for that, this is for A plus D, and for A minus D, because here we don't know what happened here, then we can assume that. So if we assume that K squared less than Q, if you for K squared less than Q, so we have negative on the left side, so which means we have A minus D squared plus B 4BC. For BC, this is negative. Okay, if it's positive, then we have we don't have a solution. Just what is it? Okay, if that one positive, we have different. Okay, so if both are negative, so we have that one is negative, so then the 0, 0 is a stable spiral point, is a stable spiral point. Okay, and so remember that we have, in this case, where is our critical point here? One is when n is 0, so we have 0, 0. If n equal to 1, so we have pi 0. So which means if you have n negative 1, sorry, n is 1, so we have plus and minus, of course. So for the critical point, we have 0, this is our critical point, and we have pi here, and we have negative pi here. Yeah, for pi, we have a stable spiral point, so which means we have that. The stable means it goes inside. Okay, now we need to determine what happened there. For that part, I just leave it to you. For this part, I will show how to do it. So what we can do now, for this part, the best thing is we transform the coordinate. So means that instead of we have center at 0, 0, now let's say we have a center there. So how to do that? We do a transformation, change of variable. Alright, so for theta equal to phi plus pi. So that will change from 0, 0 to pi. Okay? Can you see this thing? Okay. So that 0, 0. This is the critical point from the critical point that I gave earlier. Alright. I've done that part for the pi. Alright. So we do the transformation so that we have the center becomes 0 pi becomes center. Alright. And then this is the transformation that we need. Then okay, so we change the variable, do transformation or change the variable. Let theta equal to phi plus pi. So that we have the equation phi double dot plus 2k phi minus q sine phi that equal to 0 for k positive and q positive. Okay, so what happened, this transformation is that now instead of we have theta 0 pi here, this transformation will give or will transform your coordinate system into that 0, 0, 0 pi, this point to 0, 0 here, to 0, 0. So this point becomes that. It's not difficult to see. Yeah, when theta is pi, so phi got 0. Okay, so by doing this and do the same analysis as we did earlier, then we have the 0, 0, which is in this case, in the original case is 0 pi. So this is a saddle point. A saddle point. So therefore, this is the transform one, yeah? The transform one. So which means the original one we have, which is pi 0, is a saddle point. Is a saddle point. So from there we have, this is 0, 0. We have the spiral here, alright, which is stable, goes inside. And then at pi 0, we have a saddle point. You know what saddle point is? So we have something like that, and that. And since those arrow to the into the critical point, so you just follow this arrow. Okay, so we have that, and this, it goes like that. So we have that, here it goes like that, and here we have that. Then you can have more, you can have more, you can have more. That give you, oops, sorry, this side. Okay, so this is the phase portrait of the system for the pendulum. You can do on the what happened on the left side. Try that. And this, I think you can do the transformation theta equal to phi minus pi. If you do this transformation, then you got 0, 0 this point. Then you can determine the behavior of the trajectory at those points. Okay, now let me give you one more example. I have in my notes here we have another example here. We consider this system example. So x dot equal to y and y dot equal to 2x minus x squared. So it is easy to see in this case. Here we have a is 0, b is 1, c is 2, d is 0. Right? So which give you ad minus bc, this is different than 0. So it satisfies our condition. Where and your epsilon 1 is 0 and your epsilon 2 is negative x squared. And to find the critical points, equate that equal to 0, equate that equal to 0. So you have the critical point for the 0. So this is x equal to 0 and x equal to 2, right? So which means your critical point is 0, 0 and 2, 0. Okay. Okay, now if you look at the condition for epsilon 1 and epsilon 1 and epsilon 2, so it is obvious that 0, 0 is a simple critical point. Here, look at the system itself, especially zeta 1 and zeta 2. Epsilon 1 and epsilon 2. Yeah, and it is a saddle point. Okay, it is a saddle point. Now we have done that at that point. So this is the saddle point. We know the saddle point is like that. So like that, and that. Okay. Now this is 0, 0. Now we need to determine at the 2, 0. 2, 0 is here. This is x2. So we need to determine what happened, the trajectory at 0, 0. Okay. So if we make the transformation, let x equal to z plus 2, then we have the system. So these systems, we have z dot equal to y and y dot equal to minus 2z minus z squared. Just substitute this into our system here. Okay, then you have that system. Again, we can analyze that system. Consider the linear part. Okay, the corresponding linear system is z dot equal to y dot equal to minus 2z. Okay, just consider this. So in this case, we have 0, 0 is the critical point for that. Okay, 0, 0. Then what we have? So 0, 0. So we have 0, 0. We need to determine this thing, either it's saddle point or what. So we have, you can check those things. A equal to 0, b equal to 1, c equal to 0, d equal to minus 2. Alright, and as well you can check what is it? A minus d squared plus 4bc. Okay, and so on and so forth. So I just having done all those things, I just go to the so we have 0 0 is a center. Yeah, 0 0 is a center, so which means this center for the transform system, all right, but for the original system that we deal with, which is 2 0, this is the center to the original system. Yeah, center for original system. So which means we have at 0 0 we have a saddle point. Yeah, 0 0 we have a saddle point, so we have that, and at 2 0 we have center, so just that's a center. Okay, and you look at the direction, it goes to clockwise. So for the saddle, you just follow those arrow. So we have those arrow, so which means it goes that side, it goes that way, that and that, and that. Okay, so just you add some more point here, some more line there, so you can have the trajectory. Okay, so that for the example. So for the detail here, I think you just follow what we have done earlier. You just check one by one each condition, then you can determine that 0 0 is a center. This is for the transform one, but comes to the original, because this is the one that we are looking for. So with this we can conclude for the original. So this is this trajectories or phase portrait for the corresponding linear system is also applied for the non-linear system that we dealt with. Okay, so I have two examples. I've shown you two examples. Now in your notes, we also have some exercise for you. Please do that exercise. And also, if you want extra exercise, I can give you. Just a minute. Let me look at the book. I use this book is quite okay. I think this chapter 11, if I'm not mistaken. You can look at this book. Differential equation by theory, technique, and practice by George. This is the name. Yeah. Simon and Kranz. Yeah. Let me give you, if I can find, quite good explanation in this book. Some for the nonlinear system. Yeah, I just put here for you for the exercise. Okay, that's up to number 4. Then for numbers, we have another 5 6 you can try, but those things might be a little bit difficult, but try that. How to get those close to it? Just a minute. Oh, kena. Macam mana nak buat ni? Oh, I cannot get the 5 to 6. You just take 1 to 4. Enough. Alright. 1 to 4. That's number 4. Or I have to remove this thing from there.